Hello everyone, I'm Dr. Shanmuga Sundari, working as an assistant professor at PG and Research Department of Physics at Sita Lakshmi Ramaswamy College, Tiruchirappalli. So here as a continuation of our previous section, we are going to see how the normalization and orthogonality of the wave function will be for the particle in one-dimensional box. I'll give you the quick recap. We just consider the particle which is inside this region 2, and we consider the potential energy is 0 for this region 2, and for the other two region, that is when x is less than 0 and x is greater than a, the potential energy is infinite. Even at the boundaries, the potential energy is infinite. For such particle, the wave function psi of x is given by a into sine of n pi x by a. So for this equation is true only for when the particle is between the region 0 to a, and the psi of x is vanishes for the region when x is less than 0 and when x is greater than a. So for this particular problem, we are just going to see the normalized wave function. And we are very sure it is possible to find the particle only in this region 2. And in this region 2 and 3, definitely we could not see the particle. And so the psi of x is equal to a into sine n pi x by a is having a definite probability between the region when x is less than a and it should be greater than 0. And for the all other region, psi of x is equal to 0. It means when x is less than 0 and x is greater than a. So it is having a definite probability for all the time to find the particle in this region 2. So we can write that 0 to a, the modulus of this psi square of x into dx is equal to 1. So using this condition, we are going to calculate the normalized wave function for this one-dimensional potential box. So this can be written as integral 0 to a square sine square n pi x by a into dx is equal to 1. It is not possible to find the integration of sine square n pi x by a. So this can be written as 0 to a square by 2, 1 minus cos 2 n pi x by a into dx is equal to 1. So this integration can be written as, I can take this a square by 2 as a common, then 0 to a into dx minus 0 to a cos 2 n pi x by a into dx, and that is equal to 1. So now doing the integration, I can calculate a square by 2 into x 0 to a minus. So when I'm differentiating this cos 2x, then I'll get sine 2 n pi x by a into what? A by 2 n pi, then the 0 to a, and that is equal to 1. And we know that sine of n pi is equal to 0. So the second term becomes a 0. So we can write a square a by 2 is equal to 1, or I can write a square is equal to 2 by a. From this I can get a is equal to square root of 2 by a. So by substituting this a in our wave function, I'll get the normalized wave function sin of x is equal to square root of 2 by a sine n pi by x n pi by a into x. So now I'm going to draw the normalized wave function for the first three states to get the clarity. So here that the boundaries is that x is equal to 0 and that x is equal to a. So for the first wave function, that means that psi 1 of x, it is having two nodes. One is at x is equal to 0 and another one is at x is equal to a. And for the second wave function, that is psi 2 of x, it is going to have three nodes. One is at x is equal to 0 and the second one is at a by 2, and the third one is at x is equal to a. And similarly, for the third state of our wave function psi 3 of x, it is going to have 5 nodes. So it means that the wave function is having n plus 1 nodes. The normalized wave functions are having n plus 1 nodes. So the next we are going to see about the orthogonality of this wave function. Orthogonality of the wave function. So for that I'm just going to consider two wave function. One is psi m and psi n in the same limit 0 to a. So I'm just going to describe the psi n as nothing but square root of 2 by a sine n by x by a, and similarly psi m can be defined as 2 by a sine m by x by a, and here the psi n and psi m are the real wave functions. It means psi n star of x is nothing but psi n of x, and similarly psi m star of x is equal to psi m of x. And here one more thing is n is not is equal to m. So I'm just going to calculate in the same limit 0 to a psi m star into psi n into dx. So in that case it is going to be, if I'm going to substitute the psi m and psi n value, then I'll be getting sine m pi x by a, then sine n pi x by a into dx. Yes, it is on the same limit 0 to a. So I'm going to write the same equation, which is nothing but 0 to a 2 by a sine m pi x by a into sine n pi x by a into dx. So here we are just going to use a formula called 2 sine a to sine b is equal to cos a minus b minus cos a plus b. So using this formula, we are just going to find the value of the above integration. So which is going to be 0 to a integration 0 to a cos m minus n into pi x by a minus cos m plus n pi x by a into dx. So now this can be written as what? 1 by a 0 to a. I'm just going to separate this integration pi x by a into dx minus 0 to a cos m plus n into pi x by a into dx. Okay. So by integrating this, we are going to get 1 by a. Then it has become what? Sine m minus n by pi into then a by m minus n into pi, then the limit 0 to a. Similarly, for the second term, it is going to be sine m plus n by a into pi x. Similarly, here also we are going to have ax into a by m plus n into pi, then the limit of integration 0 to a. Okay. So here the both the terms for both the limits 0 and a, it's going to vanish. It means the integration of this 0 to a psi m star psi n dx is equal to 0, or it is like 0 to a psi m star psi n dx is equal to 0. It shows that the wave function psi m and psi n are orthogonal to each other in the limit 0 to a, and we know that in the same limit they are normal to each other also. So they are orthonormal functions, and even after these limits, I mean when x is greater than a or when x is less than 0, we couldn't find the particle. In that case also psi n of x is equal to 0. So we can say for the whole limit, means minus infinite to plus infinite, for the whole limit, the wave function psi n of x is orthogonal function. Yes, thank you for listening. Thank you very much.